Okay, this is very much like an example that you've probably already seen, where what we want to do is cut the corners out of a rectangular sheet of cardboard or paper, fold up the sides to create a box. All right, in the traditional problem, you're going to maximize the volume in that box. This problem involves a twist, but there's a twist with a message at the end. All right, what we want to do is maximize the combined volume of the original box that we constructed, and then we're going to take these four corners and tape them together in a four-sided box shaped like a cube. Right. And we want to maximize the combined volume of the original box, the tray, plus this cardboard or paper pencil holder type box. And so the combined volume, let's see here. This side will be 8.5 minus 2x. This distance, the length of the box, is 11 minus 2x. So the volume of the tray is 11 minus 2x, 8.5 minus 2x, times x, plus we have to combine that with the volume of the pencil holder, x cubed. Alright, if you FOIL this all out and you're a little bit patient, you'll find that this is equal to 5x cubed minus 39x squared. By FOIL, I mean multiply this out. You can't really FOIL a cubic, though that could be one of the steps in multiplying that out. So that's the first few steps. We're up to step 3 now, where we've found our function. Actually, we've hit step 4, because now we have it in terms of one variable. What is the domain of that function? That's really important in this problem. Okay. Well, just looking at the physical problem here, I know that x has to be greater than or equal to 0, but there's also a maximum. The biggest I can make x is when I cut away half of this side here, because then I have x has to be less than or equal to 4.25. Past that, I've cut away too much, more than is physically possible. So now I have a closed interval, right? And that's important here. If I'm going to find the maximum value of a continuous function, it's a polynomial, on a closed interval, then I use the closed interval method. And the closed interval method says that we have to find the critical numbers of the function that lie inside this interval, and we're going to check the function value, the original function value, at those critical numbers and also at the endpoints. Right. So now we need a derivative. Right. The derivative here is relatively simple. It's a nice polynomial after all. Set that equal to 0 to get the critical numbers, and if you use the quadratic formula, I'm not going to show it here, but you'll get x equals 1.87 or x equals 3.33. Alright. If you were just checking critical numbers and checking the volume at those, you would find that the maximum volume occurs when x equals 1.87, but that is not the absolute max, that's merely a local max. Alright, so be careful. You have to justify that you know you found the absolute max, and that means thinking about what is the domain of the function. Does it have endpoints that I need to check? So I'm going to check the volume at each of these points. Endpoint number 1, critical point number 1, critical point number 2, and endpoint number 2. And if you compute the volume, so we can go back here and use this formula, or you can use this one, it doesn't matter. You'll find that you get 0, 71.16, 63.52, and of these two values, this is clearly the larger, but when I check this last value, I get 76.77, and that would be cubic inches. And because the absolute maximum has to occur at an endpoint or a critical number, I found the absolute maximum. All right. Weirdly enough, it happens when x is equal to 4.25. So what am I doing? I'm going to cut half of this side off into 2 squares, half of this side off into 2 squares, and I'm going to fold it up and make a pencil holder. And I have no corners here now, so this middle part I'm just going to discard. All right. and that gives me the most possible volume. Right. That might make a little sense to you if you think, well, this sheet of paper is kind of close to a square already. All right, so I can get some really big squares out of the corners without wasting much material. All right. And it's more efficient to build this design because it's only got 4 sides. I can encompass more volume than it is to build this, the tray design. All right, because it's got, I also have to account for the bottom here, so I've got to use some of my material for that bottom. Right. In this case, I do best by putting all my energy into building the pencil holder. All right. So we're going to cut large squares, largest squares, and build only a pencil holder. All right, and your intuition here might be that if there isn't much waste, it's more efficient to build a 4-sided box than it is to build a 5-sided box. All right. This answer changes, all right, depending on the geometry of the paper. So if I use a 6x10 sheet of paper, that's a little more rectangular. It's longer and narrower in terms of its shape. All right. And if we go through the same math, we're not going to be careful here. All right. You'd have x times 10 minus 2x, 6 minus 2x, plus x cubed. FOIL that out. FOIL that, I mean multiply it out. Right. Take the derivative. Right. I didn't mention the domain here, but the domain, the largest I can make the x is 3 because then I've cut away one side of the paper. Set that equal to 0 and use your quadratic formula to get your roots. And you get x is equal to 1.39 or x equals 2.86. So again, we have 2 critical numbers to check, and then we have the 2 endpoints. We're going to compute the volume at all those points, and it goes like this. In this case, the interior maximum that occurs at the first critical number is the absolute max. All right. I think what's happening here is we have a piece of paper which has a narrower aspect ratio. Okay. And so it makes sense in this case to cut some smaller corners out and build a smaller pencil holder, and you're still left with a relatively large tray. All right, and that's how you get the absolute maximum volume of 35 cubic inches.